Massive black hole collision detected, largest merger ever. Hold onto your telescopes, astronomers just witnessed the most colossal cosmic collision ever recorded, and it's rewriting everything we thought we knew about black holes. This monumental discovery of two black holes slamming together challenges fundamental theories about how these cosmic giants form. Let's break down what makes GW231123 so revolutionary. Using ultra-sensitive detectors called LIGO in the US, Virgo in Italy, and CAGRA in Japan, scientists caught ripples in spacetime from a violent merger where each black hole weighed over 100 times our sun's mass. These ripples, known as gravitational waves, were predicted by Einstein over a century ago but only first detected in 2016. What's astonishing is that this single event dwarfs the previous record holder by nearly 40% in total mass. Here's where things get truly mind-bending: these black holes shouldn't exist according to standard cosmic rules. Normally, black holes form when massive stars collapse. But here's the catch: there's a theoretical mass gap between about 60 and 130 solar masses where stellar collapse shouldn't produce black holes. Yet both GW231123 black holes sit squarely in this forbidden zone. As if that weren't puzzling enough, they're spinning at almost the maximum speed physically possible. So how did these cosmic heavyweights form? Leading theorists propose a cosmic chain reaction. These might be second-generation black holes created from earlier mergers. Imagine two smaller black holes colliding to form one, which then crashes into another, creating progressively heavier giants. This would explain both the unusual mass and crazy spin speeds. But here's the controversial part: could alternative theories explain this better? Some suggest direct collapse of supermassive stars or intense collisions in star clusters. What's your take? Do you think we're seeing cosmic recycling in action, or is something even stranger happening? Gravitational waves remain our only window into these invisible collisions. Unlike light-based telescopes, they detect warps in spacetime itself. The detectors are so sensitive they're measuring movements thousands of times smaller than an atomic nucleus. Though we can't pinpoint GW231123's exact location, it might be up to 12 billion light-years away. We know its colossal scale: one black hole was about 100 solar masses, the other roughly 140. This discovery hints at a hidden population of mid-sized black holes bridging the gap between star-sized ones and supermassive giants at galaxy centers. Future observatories like the Cosmic Explorer and Einstein Telescope will test these theories further. As one researcher put it, we've moved from first detection to challenging our best theories in less than a decade. Now over to you: do these impossible black holes suggest our models need a major overhaul? Could there be entire populations of black holes formed through cosmic mergers? Share your thoughts below. Heaviest black hole merger shatters physics, inside the forbidden mass gap. Breaking boundaries: the most massive black hole merger challenges long-held astrophysical beliefs. A landmark discovery is shaking the foundations of black hole science, revealing a merger between black holes so massive that it defies the well-established theories of how these cosmic giants form. The recent detection, involving black holes weighing roughly 100 times the mass of our Sun each, falls into a mysterious mass range traditionally considered unreachable by standard stellar evolution processes. This intriguing finding points to the possibility that some black holes are born through complex, multi-step merger events, an idea that challenges conventional wisdom. Since 2015, when the first black hole merger was detected through gravitational waves, researchers have catalogued over 300 such events courtesy of the LIGO Virgo CAGRA (LVK) collaboration. This international effort employs cutting-edge gravitational wave observatories located across the United States, Europe, and Japan. These instruments detect the faint ripples in spacetime created when two black holes spiral closer and eventually coalesce. Typically, these black holes weigh around 10 times the Sun's mass, a size well explained by the classic stellar collapse model, in which a massive star exhausts its nuclear fuel and collapses under its own gravity into a black hole. But things get complicated with the most massive stars. Theory tells us that stars with masses around 200 times that of the Sun become unstable because the extreme conditions at their cores lead to the creation of electron-positron pairs, tiny particles of matter and antimatter. This process significantly diminishes the internal pressure that normally keeps the star from collapsing, causing a violent implosion instead of a gentle collapse to a black hole. This phenomenon creates what physicists call the pair instability mass gap, meaning no black holes should form in the mass range between about 60 and 130 solar masses. Yet, the universe often surprises us. Back in 2019, the LVK collaboration caught a glimpse of black holes merging whose masses, at 65 and 85 solar masses, appeared just inside this forbidden gap, sparking debates over whether alternative formation pathways might exist. Because the exact boundaries of the mass gap weren't perfectly defined, some scientists speculated these black holes might still have formed from unusual stellar collapse scenarios. Fast forward to November 2023, and the LVK collaboration has upended our understanding even further with the event designated GW231123. Detected by LIGO's twin observatories in the US, this merger involved black holes even heavier, one firmly situated within the mass gap. Stephen Firehurst, spokesperson for the LIGO scientific collaboration and based at Cardiff University, declares, "This event provides compelling evidence that black holes residing in the mass gap are real and do exist." What makes GW231123 a headline grabber is not just the extraordinary masses involved, 103 and 137 times our Sun's mass respectively, but also the sheer size of the final black hole formed, a whopping 225 solar masses. The gravitational wave signal was notably brief, lasting only about a fifth of a second, and was detected primarily in the detector's low-frequency range, a signature typical of heavy, massive black holes. This brevity presented significant challenges in decoding the data, reducing the amount of detailed information available to researchers, as pointed out by LVK member Sophie Binney from Caltech. The standard wave pattern models these scientists use to tease out key properties like mass, spin, and position in space become less reliable when faced with such limited data. Despite these hurdles, the team's analysis is robust enough to declare the masses and spins with reasonable confidence. Interestingly, one unresolved point was the inability to pinpoint where in the sky the merger occurred, leaving some mystery about its cosmic neighborhood. Binney shared the collaborative findings recently at the GR Amaldi conference in Glasgow, Scotland. Astrophysicist Davide Gerosa of the University of Milano Bicocca, who was not part of the study, passionately remarks, "This is truly exhilarating. When gravitational wave astronomy started a decade ago, black holes around 30 solar masses astonished us. Now we're seeing black holes exceeding 100 solar masses. It's a whole new scale of astrophysical wonder." So, how did these behemoths come to be? One leading explanation is the idea of hierarchical mergers. This fascinating process envisions black holes born from earlier mergers clashing again with others, gradually building up to colossal sizes. Binney likens it to a genealogical family tree of black holes, where the descendants can reach unprecedented masses through multiple staged mergings. However, there's a complication. Post-merger, the newly combined black hole often receives a so-called recoil kick, a gravitational slingshot effect that might eject it from the dense star-packed regions needed to facilitate further merging. This dynamic poses an ongoing puzzle for astrophysicists. An insightful clue comes from studying the spin, the angular momentum, of the black holes involved. If these black holes form directly from stars in a binary system, their spin axes should be mostly aligned and relatively low due to the star's mutual gravitational influence. And indeed, most black holes detected by LVK fit this pattern. However, the final black hole resulting from the merger usually spins much faster, as it inherits the orbital angular momentum from its progenitors in the binary dance. In GW231123's case, despite substantial uncertainties in measuring spin, ranging from 20% to 50%, both component black holes appear to be spinning near their theoretical maximum, approximately 80% and 90% of the maximum spin rate allowable by physics. Such high spins are widely interpreted as a fingerprint of prior merger events, reinforcing the hierarchical merger scenario. Yet, Gerosa notes something thought-provoking: with spins this high, the numbers slightly exceed the usual expectations for hierarchical mergers, which typically predict about 70%. It may be that future refinements in data analysis will adjust these spin estimates downward, he suggests. An alternative possibility entertained by the LVK team is that these supermassive black holes might have formed when two massive stars merged directly, thereby sidestepping the pair instability barrier. But this explanation struggles to align with the observed high spin values for these black holes. Even if the precise formation routes remain uncertain, understanding the birth environment of GW231123 may shed light on these cosmic mysteries. According to theorist Rosalba Perna from Stony Brook University, also unaffiliated with the research paper, the merger probably took place in a dense stellar environment where black holes encounter each other frequently or within a thick, gas-rich setting, enabling black holes to accumulate substantial mass through accretion. She points to the disks surrounding active galactic nuclei as plausible locations for such dramatic black hole growth and interactions. But here's where it gets controversial. If these enormous black holes really form through hierarchical mergers, what does that imply about the life cycle of black holes and the dynamics within dense cosmic neighborhoods? Could there be a whole population of massive black holes hiding in plain sight, just waiting for the right conditions to collide? Or does this challenge our understanding of stellar physics and black hole formation fundamentally?